Now the theoretical portions from the last module, it actually deals with the flight performance during the flight of a rocket. So we're going to see two different kinds of equations. So one is equation for the maximum velocity reached by a rocket, so after flying for a certain distance, and the second one is like the maximum height reached by the rocket. So this general expression is known as a rocket equation, and these two derivations are important because derivation itself can be asked for the final exam. So here, when you're going for the deriving the rocket equation, the basic assumption what you're going to take is like first of all, the flight is assumed to be vertical. Like we are going to consider only vertical flights, and the drag force, total drag force, is assumed to be 0 because also why the drag force is because like whenever a rocket flies, obviously drag force will be there because air resistance will be there. Now why it is taken as 0 is because the drag force actually depends upon the height. So if the height increases, obviously the presence of air will be less, so the force or the opposing force is going to be reduced. That is why after certain height the drag force can be assumed to be negligible. So for the total derivation anyway, we are going to take like the total drag force is 0. Now the flow through the nozzle is steady and one dimensional, so that a steady thrust is produced, and the third assumption is the specific impulse and the gravitational force are assumed to be constant. So G value is assumed to be constant, or the pull up on the rocket in the downward direction is assumed to be constant. So these are the three assumptions. So this you need to mention before going for the actual derivation. Now the thrust developed by the vehicle providing accelerating and for overcoming the gravitational force. So the total thrust produced by the engine F will be equal to ma plus mg. So m into a is the thrust which is produced for taking the vehicle in the forward direction or in the upward direction with an acceleration a, and mg, it is the total gravitational pull. So in order to overcome mg, so the engine need to do additional work. So the total thrust developed by the engine will be utilized for accelerating the vehicle, that is the first part, and it is utilized for overcoming the gravitational pull. Now let m be the mass of the vehicle at any time t. If m1 is the initial mass of the vehicle before starting the flight, so m1 is the initial mass and m2 is the final mass. So after reaching or after passing a total flight time of t suffix p, the total weight of the vehicle is m2. So m1 is the initial one and m2 is the final mass. So once after burning out the entire propellant, the final mass is m2. So m is actually, it is for representing an intermediate mass. So after any time of flight of t, let m be the mass. So from m1 and m2 you can obtain m value, that is, or m1 minus m dot p. So that expression will see m dot p into vp will give the total m2 value. So this expression will see actually. So there can be a relation between m1, m2 and m value. So vp is the final velocity of the rocket. This is actually what we need to find out. So m1, that is the initial mass of the rocket, m2 is the final mass. So once after a time of tp, at specified time of tp, let m2 be the final mass of the vehicle and m is the intermediate mass at any time in between t is equal to 0 and t is equal to tp. So at any instant t, m is the mass. So the total thrust produced will be equal for utilized for producing the thrust on the rocket or producing acceleration for the vehicle, that is m into a plus overcoming friction. So a will be equal to d into v by dt. That's a derivative velocity, so dv by dt. So the expression can be written as f is equal to m into dv by dt plus mg. Now from the definition for specific impulse, like specific impulse was f by m dot p, that is the thrust force by unit mass propellant consumption rate. So ISP is a specific impulse and m dot p is the rate of consumption of the propellant. Now m dot p can be written as, it is a rate of consumption of fuel or the propellant. So during the operation of the rocket, if the mass reduces from m1 to m2, so that reduction time m1 minus m2 by total time duration, so that is actually the consumption of the propellant. So it will be equal to dm by dt. So the minus sign is because the mass of the vehicle is reducing, that is why this minus sign is given. So m dot p is equal to the rate of reduction in mass over a time period of dt. So the thrust force will be equal to, so this, if you substitute in this value in this expression, F is equal to minus isp into dm by dt. So this value for F is given in the first expression, which I think we had seen. So here, so m into v dv by dt plus mg will be equal to this value minus isp into dm by dt. So this is going to be written in the differential form. So if you multiply the entire equation using dt by m, so the first term will be dv itself. So g m will get cancelled. G into dt will be equal to minus isp into dm by m. So you need to find an expression for Vp, that is the final velocity of the rocket. So if you integrate this term within the limit, so the velocity is going to be changed from 0 to Vp. So the initial velocity is 0 and the final velocity will be Vp. So the first term will be integral 0 to Vp dv. Now the second time is going to be changed from 0 to Tp. So g into integral 0 to Tp dt will be equal to minus isp into the mass. The initial mass will be m1 and the final mass will be m2 into dm by m. So this will be Vp into g into Tp will be equal to isp into, so this will be actually logarithm, integral will be logarithm of m over the limit m2 by m1. So minus, if it is taken inside, this will be isp into ln m1 by m2. So this can be again written as Vp will be equal to isp, that is a specific impulse, into logarithm of m1 by m2 minus gtp. So this is actually the rocket equation. Now m1, it is actually the initial mass and m2 will be the final mass. Tp, it is over the period of time through which you are going to analyze. So after time Tp, the rocket is going to be acquire a velocity of Vp. So m1 is the initial mass of the vehicle, which includes mass of the structure plus payload and all those things. m2 is the final mass excluding the mass of the fuel which is being burned. So m2 can be written as, the final mass will be equal to the initial mass minus the mass of the propellant, how much it is being consumed over a time of Tp. So m2 by m1 term, that is known as the ratio, that is the final mass by initial mass of the rocket, that will be mass ratio. So the Vp can be written as isp into, so this term is m1 by m2 or 1 by m2 by m1. So this isp into ln 1 by mr minus g into gp. So this is another form of rocket equation in terms of mass ratio. Now if the flight is happening in the outer space, obviously g value will be 0. So this second term will be 0. So final velocity will be equal to isp into ln ampere. So whether in the question, if it is given that, so just to find out the condition when the flight is happening in the outer space, then you don't need to consider this value at all. So Vp will be equal to isp into ln ampere. Anyway, Vp, this value, this equation 4 is considered as the rocket equation, so which will actually give the final velocity of the rocket in terms of the specific impulse, mass ratio and the total time of propulsion. So that is the first part, and the second one is the altitude gain during the vertical flight. So after a time Tp, so how much altitude is going to be attained by the rocket, or how much distance is going to be covered by the rocket in the vertical direction. So it is the second part. So the rocket equation was V is equal to isp into ln m1 by m2 minus g into Tp. So assume that if you consider in the case after a time t in between 0 and Tp, so at that instant the mass of the rocket will be equal to m and the time is t itself. So V will be equal to isp into ln m1 by, instead of m2 you are using an arbitrary time t, and that condition the mass will be m. So m is a mass at any instant t. So the altitude reached starting from z is equal to 0 is, so this is the expression for v. So integral over v into dt will give the altitude. So velocity into time, the total integral will give this one. So isp into the first term integral 0 to t ln m1 by m dt minus g into integral 0 to t, because time is going to be changed from 0 to t. So isp into integral 0 to t ln, this is the initial mass of the vehicle, and the mass at any instant t can be written as m1 minus, that is initial mass minus the rate of propellant consumption over a time t. So m dot p into t will give the total propellant consumed during a time change from 0 to t. So in the first t seconds, how much propellant, how much mass of the propellant is being consumed, that is m dot p is the rate of consumption, that into total time will give the total propellant consumed over a time t. So m1 minus that time will give the final mass, or the mass of the mass of the rocket after a time t. So that into dt minus g into integral 0 to t into t. So again this one will be equal to ISP into integral 0 to t ln m1 minus integral 0 to t ln into m1 minus this time. So ln of this ratio will be equal to the logarithm difference, so difference in logarithm, minus the integral of this time will be equal to half into gt square. So the first term will be equal to ISP into, so this time is constant, so t into ln m1 minus the last time half gt square. Now the integral of this one, see if you are using the product rule, you will be able to find out the integral of u dv will be equal to uv minus integral v du. So if you use that equation, so you will get this term as the integral of ln f1 minus m dot p t into dt. So if it is difficult to find out, you just by heart this term. So that minus t over a time range of 0 to t. So if we substitute this value, ISP into ln m1 minus half gt square, so just substitute t values and just rearrange this equation. So here you are going to divide by m dot p, so this will be equal to t in minus m1 into this term, that minus t, that minus, when we substitute 0 in this expression, you will get this value. So on simplifying this term, so ISP into t will come from this one, so this ISP into t, it's minus ISP into minus t, that is the first value, minus this half gt square. So this is taken inside and you are going to combine with the similar terms. You will get t into ln m1 by m1 minus m dot p into t minus the second term. This is taken as common, ln into m1 minus this term. So this is actually the expression for altitude reached at any time t. Now when t is equal to tp, that is at the end of the total burn out, or after burnout, after the end of the total burning time, when t is equal to tp, so this time m1 minus m dot p into t will be equal to m2. So is that p will be equal to, that is the total height reached after a time of tp, or when the velocity is vp. So that will be equal to, you can substitute those values, ISP into tp into this one will be equal to, this denominator will be equal to m2. So just combine the similar terms, you are going to get this value. So just substitute this difference as m2 and rearrange the terms, you will get the total ZP will be equal to ISP into TP ln m1 by m2 minus m1 by m dot p ln TP minus half gt square. So m2 by m1, you know, it is a mass ratio, so again it can be written as, so if you are combining ISP terms, you will get Tp minus m1 by m dot p into ln1 by m bar plus this Tp minus half gt square. So this is actually the total height reached, so after the propellant consumption, so when t is equal to Tp, or when the velocity will be Vp. Now in the case of multi-stage rockets, that is about a single stage rocket. So multi-stage rocket means if there are a number of stages, so you know, like after the burning out of each and every stage, so normally the high distance rockets are of multi stages. In a single stage you cannot reach a longer distance at all, so different thrust boosters you are going to ignite in between the operations. So after igniting each and every booster, obviously the distance and velocity is going to be changed. So in the case of multi-stage rockets, the final velocity Vf will be equal to V1 plus V2 plus etc. Vn, because V1 is the total velocity after the burning out of the first stage, V2 is the second stage, and etc. Vn is the nth stage. So if it is a 3-stage rocket, obviously V1 plus V2 plus V3 it will come. So Vf, the expression is ISP1 into ln m by 1 by mr. So that g time we are going to avoid, because if the flight is happening at the outer space, so Vf will be is equal to ISP1, that is the thrust in the first stage, ln 1 by mr1. mr1 means it is a ratio, that is a final mass after the burning out of the first stage divided by initial mass. So on second and so on. So this individual velocity, if you add, you will get the final velocity of the rocket. Similarly, so if you combine these two equations, this is ISP into ln 1 by mr1, ISP ln 1 by mr2, etc., etc. ISP is constant, so Vf into ISP into ln. So if you combine this time, 1 by mrn, 1 by mr2, 1 by mr3, etc. So 1 by mr1 means, so 1 divided by m2 by m1, or this will be equal to m1 by m2. This is 1 divided by m3 by m2, or this will be equal to m2 by m3, and so on. So just similar terms, if you are cancelling, ISP into ln m1 by mn. So if it is an n stage rocket, so the specific impulse into logarithm of the initial mass by the mass after the burning out of the nth stage, so that will give the total velocity. So if it is a 3-stage rocket, m1 by m3, so that will give Vf. So that is the way in which you need to find out the velocity and for multi-stage rockets. So just remember these equations